Aloha, my name is Jordan Kajiwara. I'm a first year freshman at the University of Hawaii, MANOA, and I will be majoring in mechanical engineering.
And my name is Chaitin Liu. I am also a first year freshman at UH Manoa, and I will be majoring in electrical engineering.
Together, Chaitin and I will be working with Evan Kawamura under the supervision of Dr. Dilmurat Asmov, and we will be simulating drone stabilization on the moon.
So a little overview of what our lab has done over summer. So what we've been doing is simulating drone stabilization for exploring space. And why we need drones to explore space in the first place is because rovers can only cover so much ground over a certain period of time. And one example of this would be the Curiosity rover, which is currently on Mars, whose top speed is only 0.09 miles per hour, compared to the Mavic 2 Pro drone, which is the drone that we'll be using for our simulations, whose top speed is 44.7 miles per hour. And if you did some math, after half an hour, the Curiosity rover covers about 0.05 miles compared to the Mavic 2 Pro, which covers 22.36 miles or 35 miles. Sorry. So as you can see, that's a pretty significant gap in the amount of ground that can be covered between the two. Okay, so a couple of benefits for using drones is they allow us to explore previously inaccessible locations. And examples of this would be, say you're on the moon and you're doing exploration and there's a crater, and if you had a rover, the rover would have to either go around or go through the crater, which would take a while. But if you had a drone, the drone would just be able to fly over, and it would allow for a lot more efficient exploration. And drones are also a lot more cost efficient. And one example of this would be the Curiosity rover again, and the Dragonfly drone. So the Curiosity rover costed $2.5 billion to make, compared to the Dragonfly drone, which costs only, or which will cost only $1 billion. And another example of this too, so for the drone that we're using, the DJI Mavic 2 Pro, that only costs $1,600 to buy.
So our primary goal in this lab was to first figure out if it's even possible for a drone to stabilize on the moon. And then once we do, it can be used to aid in lunar exploration missions like the Artemis mission expected to launch in 2021.
Okay, so a couple of goals that we had for the project over this summer. So our first goal was to determine if quadcopter stabilization on the moon was possible, and then if so, to calculate the conditions needed to achieve that drone stabilization. So for those first two goals, all we really had to do was to solve some equations and plug in some numbers, and then what would happen is we would get an upper and a lower bound for how fast or how slow the drone would need to spin in order to stabilize on the moon. And then the next goal we had was to study how different conditions affected stabilization. So in order to do this, we would just run a code in MATLAB and change certain constants. And the constants that we changed were these two constants, KD and B, which we'll go over more later. But real quickly, KD is the constant for drag force, and B is the coefficient or the drag coefficient for torque. So we would pretty much just change those two coefficients and see how that would affect the drone stabilizing.
So as Drayton said earlier, the drone we will be using is a DJI Mavic 2 Pro, and DJI is a Chinese-based technology company, and they have the #1 consumer drones in the world. They have a wide range of drones that anyone can buy at a really affordable price, and people use them professionally for like businesses and commercials, and they also use them for hobbies like Instagram and YouTube pages. They are very easy to fly and take little to no training to operate, which makes them appeal to everyone. And these are some of the specs for the DJI Mavic 2 Pro. The arm length from the center of the body to each propeller, how much the drone weighs, the battery voltage of the drone, and the motor kV value. And motor kV kind of indicates the number of revolutions a motor makes when 1 volt current is applied to it without any load attached to the motor. So it's pretty much how fast the motor can spin with 1 volt with no weight on it. And then we also found the max motor spin rate, or the MMSR, to be about 6 million radians per second. That is how fast each motor can spin.
Okay, so one of the important things when we're talking about drone stabilization is to define what stability really is. So for our project, we have defined stability as having achieved zero angular velocity after random initial orientation. So what this zero angular velocity is having no change in the roll, pitch, and yaw with respect to time. So what roll, pitch, and yaw are, as you can see in the diagram to the left, are the longitudinal, lateral, and vertical axes respectively. So as long as the quadcopter is not changing its orientation at all and is not uh, moving along those three axes as it's flying, then the quadcopter is considered stable.
Okay, for our methodology, we first calculated the MMSR, or the max motor spin rate, which we showed to be about 6 million in a previous slide. And we did this by multiplying the kV value of the drone times the battery voltage, and we got revolutions per minute. And then we had to convert this into radians per second. And then that whole quantity squared gave us the MMSR of 6 million. And that just gave us how fast the motors are able to spin. And then we had to find the minimum motor spin rate on the moon. And we did this by using this formula, mg over 4k. And where m is the mass of the drone, g is gravity on the moon, and k is just a thrust coefficient. And the values we use for g and k are shown below. And from this formula, we got 122,445 radians per second squared. And that's pretty much how slow the motors are able to spin. And this kind of gave us an upper and lower bounds of how fast and how slow each motor is able to spin on the moon. And then we simulated all of this through a code that Evan gave to us that they had already written, but we changed some of the constants to kind of make it special for the moon and the drone we were using.
So what you're looking at here is just a small snapshot of what we did in MATLAB, where we changed these two constants, KD and B, where KD is the constant for drag force and B is the drag coefficient for torque. And we changed these two constants to make them as close to zero as possible so that one, the simulation would run, and two, it would be physically possible for the drone to stabilize. So the reason that we had to change these two constants is because in reality, they're actually zero. But if we plugged in zero into our simulation, it actually wouldn't run. So as I stated a little bit before, we had to make sure, or we had to get these as close to zero as possible so the simulation would run, and it would also be physically possible for the drone to stabilize. And what this and that's what the physically possible part means. So if KD and B are low enough, it would still be possible for the simulation to run, but the MMSR wouldn't fit in the inequality below. So it would either be below 122,445 or above the 6,066,411 MMSR. And if it wasn't within that inequality, it would be physically impossible for the drone to stabilize. So basically, after doing some trial and error, the lowest we got the constants to be was 1e to the negative 20 for KD and 1e to the negative 8 for B. And those two can be seen in rows 44 and rows 51. So that's the smallest the two constants could be where the simulation would run and it'd be physically possible. And the MMSR we got from that was 1.7 e to the 6 or 1.7 million. And if you did some math, and you would find that there's a buffer of about 4.36 million from the MMSR we got through simulation and the upper bound for how fast the motors of the DJI can spin. So basically, even though this buffer seems like a lot, the 4.36 million, what would happen is that even if we were to make KD and B just a little bit smaller by like a factor of 1, say, so KD became 1e to the negative 21 and B became 1e to the negative 9, what we would find is that that 4.6 million buffer would go away, and then the MMSR would then become greater than the upper bound of what we had set.
So this was all the data that we collected that was on the previous slide, and we just put it into a code in MATLAB that created this 3D graph and compared them all together. And this allowed us to more accurately observe how KD and B affected MMSR of the drone. And it's a little hard to see what's going on here. So in the next slide, it's a little more clear. So here we have the two graphs of MMSR versus B and MMSR versus KD. And B is a drag coefficient for torque in the Z direction. And as you can kind of see, the closer they got to zero, the higher the MMSR was. And this kind of surprised us because we thought like with more drag, the motors would have to spin faster and work harder, and then with less drag, they wouldn't have to work as hard. But the analogy that our mentor Evan gave us was swimming in a pool of water versus a pool of something like honey. And this kind of made sense because we're trying to think of drone stabilization, and it's a lot harder when you're in water. You have to work a lot harder to stay stable and stay afloat, rather than something in jello. You would just kind of be sitting there, not having to work as hard to stay stable. And that's kind of a good example of what's happening here. And then changing the KV value does not really affect it as much because it's more of the linear drag, and it doesn't really affect stabilization as much.
Okay, so a couple of the more important conclusions that we came to when we were looking at how different constants affected drone stabilization was that larger drag coefficients leads to slower angular velocities. And this makes sense because it's like the more drag there is, the more work you would have to put in order to move, and therefore the slower you would be going. And these slower angular velocities would lead to a faster stabilization. And this also makes sense intuitively because, as Jordan said earlier, it's like swimming in a pool of water versus swimming in a pool of honey. Because even though you have to work a lot harder to move in the honey, it's also a lot easier for you to just stay in one place, which is what we want with drone stabilization.
Okay, so for future work, one thing that we thought of was how to get the drone to and from the moon without needing any human assistance. And one thing that we kind of were thinking of was having a rover that acts like a mothership to all drones. And this is because NASA knows how to send rovers to the moon because they did that many times. So we could attach multiple drones to the rover, and that rover will act like a mothership. And then NASA will send the rover to the moon however they did every other rover. And then the drones could take off right from that rover and come land right back on it. And then that rover could also act like a main communication unit and send messages back to mission control and act like a beacon. And that drones could operate in a centralized swarm. Um, and it could have like a solar panel that could charge all the drones. And that was just something that we thought of. Another thing is a sample collecting mechanism, because as of right now, there's no way for a drone to collect samples. It's all for taking pictures and videos and doing recon stuff. So that would be a huge improvement too. And then the last thing is a more accurate model for drag, because as of right now, finding an accurate model for drag for a quadcopter is very complex, and it would be very hard to just the geometry of a drone makes it difficult to compute the drag coefficient of the drone.
So we would first like to thank Dr. Dilmurat Asimov and Evan Kawamura for helping us and mentoring us through this project, because we're definitely not be where we are right now without them. And we would also like to thank NHSEMP and Kelly Ching for helping to sponsor our summer program. And we would also like to thank NASA, the U.S. Department of Education, and the University of Hawaii at Manoa for also sponsoring either our summer programs or the project itself. So here are our references. So mahalo for listening to our presentation. And if you have any questions, please feel free to let us know in the comments below.